guys. Good morning, good afternoon, good evening, and welcome to today's class, Ace Math with Joy. So today we're going to be looking at a very interesting topic in physics as well as further mathematics, and that is motion of connected particles. So now, what are we going to be touching under this topic? What is motion of connected particles? What are the scenarios and examples? So please, I encourage you to stay tuned to the end of this video, as I assure you, you will not regret it. Whatever that is a confusion on how to solve questions or whatever, at the end of this video, I promise you, you will be satisfied. So please do well to like, do well to comment, and also share. Very quickly, what is connected particles? Now, connected particles are two or more objects linked by a string, a rope, or rod, so that the motion of one affects the others. So the essence of us being interested in these connected particles is to see how the motion of one affects the other. All right? Good. Just like a car breaks down, maybe the engine is faulty and the car is motionless. A truck comes into play and that truck is being connected to the car, maybe by a rope, using a rope. Now, how does the motion of the moving vehicle affect the car that has refused to move? So that is the essence of us studying this. All right, now very quickly, let's get to the scenario. Now we have three scenarios of these connected particles. Scenario one, we have a trailer towing a car. Just like the example I mentioned earlier, we have a trailer towing a car. This is something very common. It's something we see often. So whenever you're on the road, watch out for this. So now let's say we have the trailer or the truck somewhere here. It's usually a truck. And then we have the car. Okay, now this car broke down and couldn't move, right? So the owner of the car wants to move the car to the mechanic. So what it means is that a truck or something heavier than the car will have to move it. So since the car is motionless, it means it has only one job, and that is to follow this one that provides the pulling force. Are we together? So now we have force here and we have tension here. All right, so this car has just one job, and that is to do what? Follow the car that is providing the pulling force. Now, since this car is motionless, it means that there is no acceleration. All right, so what happens? So it depends fully on the truck. So for the car to depend on the truck, it means that the truck provides the force. So if the truck provides the force, it means that the force from this car passes through this rope, and that is tension, to this one. So this provides the acceleration. So it means they have equal acceleration and equal tension. M1A plus M2A. So since A is common, we will have M1 plus M2 times A. So this is our force, where acceleration is equal to dividing both sides by the coefficient of A. We will have acceleration to be equal to force over M1 plus M2. All right, so whenever you hear of a car being pulled by another car and we are to find force, we can just find force by adding the masses and then multiplying by acceleration, as simple as ABC. All right, now very quickly, the second scenario. which is the aspect that comes out a lot in exam. So we have a pulley fixed at a point with a string or a rope attached to it, and then the rope drops at both ends with two particles tied to the ends. So I have tension 2 here, and then I have tension 1 here. So I have M1, and then I have M2. Okay, now, so this is the second scenario, and then you can easily find this in a construction site. So this pulley is actually fixed at a point with a rope round it. So now this pulley is actually used to carry things that have weight but not excessively heavy. All right. Now, how does motion come to play here? Now, we have this. From this diagram, you will see that M1 is heavier than M2. How do I know? Now, first of all, this pulley is very smooth. Okay, so now this pulley is very smooth, and then this rope attached to it has no mass. It is very, very light, so it cannot store force at any point. Did you hear the two assumptions? The pulley is very smooth, the rope is very light, and it is not stretchy. That is inextensible. It is not stretchy, it's not elastic. All right, because somebody might be wondering, if it's elastic, what happens? If it's elastic, now imagine having an elastic rope and then you attach something at both ends. The rope, the length of the rope will do what? Will change. The acceleration will be changing at different points. All right. Okay. So now this rope is inextensible. That is, it's not elastic. It's not stretchy. It is light. That is massless. And then the pulley is very smooth. Now, with these assumptions, if M1 is heavier than M2, how do I know? Because the rope extends, is downwards here more than here. Why? Good. It can only happen when the mass or when the particle at this point is heavier than here. Because what will happen to the rope at that end is that the rope will move down this way and then go up on the other side. Do you understand? Good. So the weight will be heavier at this end of the rope. So when it is heavier at this end, if the rope moves down by a meter, for instance, it will, coming to this end, it will go up by a meter. Remember, it is not stretching. So the weight will not extend the rope. Rather, it will make the rope to tilt towards one end. So one end will look longer than the other. Why? Because the weight at that end is more. So that's the reason why M1 is greater than what? M2. So if M1 is greater than M2, what it means is that weight here, which is M1G, is greater than weight here, which is M2G. So the weight, tension is what? Tension is always what? Opposite weight. So for this to happen, it means that M1G is more than tension. Tension is what? Force on a rope or on a string. So to find the net force on this side, we will have M1G minus tension to be equal to M1A. Now remember that tension is the same on this rope. I've given you the reason because why? The pulley is very smooth, there is no friction, so we don't have any extra force to fight. 2, the rope is very light, so it cannot store force at any point. There's no external force. Also, the rope is not stretchy, so the acceleration is the same at every point. Okay, good. So when that happens, we have the same tension, we have the same acceleration. Okay, so now on the second side of the rope, remember that this rope comes down a bit here by the reason of the weight being heavier here. So as it comes down here, it will go up here. All right, good. So when it goes up here, it means that the tension is heavier than the weight. So we have tension minus M2G to be equal to the net force M2A. All right, so when we add the two, so you see these two equations I've written. If I am to find tension and acceleration, I will use these two equations, solve simultaneously for A and T at the same time. And it's a very common question on this topic. Find tension, find acceleration. So you just substitute your M1, substitute your value of your M2, and then the gravitational force, and then solve simultaneously for A and T. So moving forward, if I add these two equations, M1G minus M2G minus T plus T will give me 0, will be equal to M1A plus what? M2A. All right, so G is common here. And then A is common here. So now what if I am just asked to find acceleration? What do I do? So if I divide both sides by M1 plus M2, and that's the coefficient of acceleration. This goes, so we have our acceleration to be force due to gravitational force into M1 minus M2, the difference of the masses over their sum. As simple as that. As simple as ABC. Okay, so I don't need to start cracking my head. How do force, what do I do? Just take the difference of the particles multiplied by the gravitational force over the sum of the forces, and then you find your acceleration, and that is it. So moving forward to the third scenario, before we start solving our examples, we have mass on a plane and a hanging mass. Mass on a plane and a hanging mass. Now, this is another common aspect that comes out a lot in external exams. Okay, so this another aspect you need to understand very, very well, though it is very simple. So now in this case, this is where friction can occur. You have maybe a table, but there is a horizontal surface where one of the masses is resting on. All right. So now the one resting, this is still the rope or the string, and then we have our pulley connected to the table, and then the other end of the rope dangling or hanging. All right, good. So of course weight will always act downwards. So this is our reaction. So now let's call the first mass here M1, and then let's have this to be M2. That means this will be our tension 2, while tension 1 will be here. So in case, what if there is friction? This is where our friction will be. Friction will always be opposite tension. Right? Okay. So now this is a weight. There is a pulley attached somewhere, and then one of the weights is resting on a table. So this is it. While the other dangles freely or hangs freely. So what happens? Now the table can be rough. That's when we talk about friction, like I said earlier. And in this case, you have seen that M2 is heavier than what? M1. M2 is heavier than M1. All right. Okay, so now how do I know that M2 is heavier? Now from this diagram, you will see that this is hanging, just like I said earlier. So now as this weight is hanging, what happens is that this tension, this force here, drags the other body or mass on this table closer to the right. Do you see that now? So at this point, at the first point, we have tension to be greater than M1G and also friction to give us the net force. That's if there is friction. If there's no friction, it will be the same thing like the second case. Are we together? Good. Then in the second case, the weight is heavier, like I explained earlier. So we'll have M2G minus tension to be equal to the net force M2A. Did you get that? Okay. So okay guys, so these are the questions we're going to be solving. We have 4 questions to solve. So the first one, let's go. The first one says a truck of mass 2000 kg tows a car of mass 1000 kg. The driving force of the truck is 6000 Newton. We are to find the acceleration of the system as well as the tension in the rope. Remember I said earlier that this acceleration and tension is a common question as far as motion of connected particles is concerned. Okay, so let's quickly do the first question. So we have a truck. And then we have a smaller car that broke down being towed by the truck. Now there is a rope connecting the truck to the car. And that is where the tension lies. Tension is the force on a string or rope as the case may be. Now there is a force pulling the car, right? And the force has been provided in the question to be 6000 Newton. Now the mass of the truck was given to us as 2000 kg, while the mass of the car was given to us as 1000 kg. Okay, so now what are we asked to find? We are asked to find the acceleration as well as tension. Now remember the equation I gave under the first scenario. You know, the first scenario we gave was that of a truck towing a car. All right, and after that we discovered that force, when a truck is towing a car, the force is equal to the sum of the masses times the acceleration. All right, because the acceleration is common to the masses. Remember I said this does not have force. It's not moving. It's motionless. And anything that is motionless, the acceleration is 0. It's at a point. So if the acceleration of this is 0, the force is also 0, irrespective of the weight, the mass, right? Good. So this is one that has the force and exerts the force to this one through tension, through this rope. That is why the acceleration is the same for a truck towing a car. So now to find acceleration, dividing both sides by the sum of the masses, m1 plus m2. This side will also be divided by m1 plus m2. So now the force has been given to us as 6000 Newton. So you know the answer already. So we have 6000 over 2000 plus 1000 will give us 3000, right? So acceleration is So tension is equal to M1A. So the first mass or mass of the car 1000 kg times acceleration, and that will give us 2000 Newton, as simple as ABC. All right, moving to the next question. Question number 2. I think for us to solve, let's look at the question together again. Now the question says two masses of 8 kg and 3 kg are connected by a light string passing over a smooth pulley. So we have to find the acceleration as well as the tension, and G is to be taken as 10 meter per second squared. Okay, so let's draw to understand what we are asked to find. So we have a pulley. We have this as our pulley, and then we have the rope dropping at both ends of the pulley. The first is given as 8 kg. So if the mass is 8 kg, that means the weight will be what? 80 Newton, since we are asked to take G to be 10 meter per second squared. So we have the second, the mass of the second to be 3 kg. That's the weight will be 30 Newton. So we have tension 2 here, and then we have tension 1 here. So we are asked to find acceleration as well as tension. So you see the weight is heavier at this end of the rope. So that means weight at this point is greater than tension. So we have 80 Newton. Okay, let's leave the Newton now. 80 minus tension will give us the net force, which is MA. So our M here is 8. A is unknown, the acceleration. And the second end of the rope, you see that as this is dropping, this part of the rope is moving up. So it is able to move up because tension is greater here, dragging the rope up. So we have T minus weight, which is 30 Newton, giving us the net force of 3A. So now we have two equations in T and A. All right, so adding these two equations, just like we did in the case of the scenario, we will have 80 minus 30 to give us 50, minus T plus T is 0, while 8 plus 3 is 11A. So since we are looking for acceleration, we'll divide both sides by 11. So our A is 50 over 11 meter per second squared. All right, so to find tension, I can use any of the equations, but I think equation 2 will be lighter to use. Okay, so using the second equation, tension minus 30 is equal to 3 into 50 over 11. So simplifying, we have T to be equal to 150 over 11. I just took minus 30 to the other side, and it will become plus. All right. So the next thing is to take LCM. And the LCM of 11 and 1 is 11. So we'll have 150, 11 times 30 will give us 330. That's 3 times 11, 33. Carry the second zero, the 0 and add. So adding these two, we'll have 480 over 11 Newton. So you can go ahead and convert to your decimal or improper fraction. So moving on to the third question, let's look at the question again. Let's take a look at the question. Okay, now a mass of 3 kg rests on a rough horizontal table. So this is the third scenario. So the first question is for the first scenario, the second for the second scenario, the third is for the third scenario. Now, a mass of 3 kg rests on a rough horizontal table and is connected to a hanging mass of 5 kg. The frictional force on the 3 kg mass is 4 Newton. We are to find the acceleration and tension. Okay, so let's go. Okay, so we have a table. Of course, that table there is friction. It is not very smooth. It is not frictionless. So we have our table. Then we have a mass of 3 kg on the table. We have a pulley fixed somewhere attached to the table. Then we have the other mass hanging freely, and that is 5 kg. So we have tension 2 here on this part of the rope. We have tension 1 here. So now from the question for mass, you will see that this is heavier. So meaning that as this weight is dragging this rope to this end, tension is pulling this one closer to the right. That means tension is bigger than the weight and force and friction rather. So we have tension minus M1 minus friction to be equal to the net force M1A, right? So the friction is not proved. 30 minus friction has been given as 4 Newton is equal to 3A. So our second equation, weight is heavier. So we have 50, that's 5 times 10, minus tension, there's no friction on that end, to be equal to 5A. So that second equation, if I rearrange, minus 30 minus 4 will give us what? Minus 36. Then this t is positive, plus t is equal to 3A. So if I add the two equations, minus t plus t will give us 0, and then we'll have 8A. Dividing both sides by 8, the coefficient of A, we'll have our acceleration to be equal to 2 meter per second squared. So the next thing is to find our tension, and we can use any equation there to do that. So we have minus 34, anyone we use will still get the same thing, plus t is equal to 3 times 2 is 6, right? So if I carried my minus 34 to this side, it will become positive, crossing the equality sign. So we have 6 plus 34. So tension is 40 Newton. As simple as ABC. So the last but not the least, let's look at that last question together. Question number 4. To rest on the plane, YB hangs freely from the edge of the plane with the string taut. The string taut means the string is not stretching, right? Particle A is released from rest and accelerates up the plane at 2 meters per second squared. That's acceleration is given. We are to find the tension and the coefficient of friction. Okay, so let's start. Question number 4. So we have a plane that's established, and that plane makes an angle of 40 degrees with the horizontal. So let's have our horizontal 40 degrees. Okay, now there is a pulley attached at the top of the plane. They said the pulley is attached at the top of the plane. Okay. So now once end of the rope carrying the weight is resting here, and the one resting here is that one that has a weight of 2 kg. The other end of the rope has the heavier weight, which is hanging or dangling, and the weight is 3 kg. All right, so for us to find the coefficient of friction, it means there's friction this way. The plane is rough, it's not smooth. All right, okay, so there's friction this way. So I believe you've seen my video on motion along an inclined plane. This is reaction. Of course, weight acts downwards. So we have it here. So we have our tension 2. We have our tension 1. All right. So we are not asked to take G to be 10 meter or anything in the question. So I'm going to be using G as 10. So I will have 20 here. That's my weight. Then I will have 30 here. That's my weight. I don't want to use 9.8 to avoid decimal since I'm not asked to. Okay, so now the question, to find tension, we use either of the equations. All right. So at this point, weight is heavier than tension here, right? So that is 30 minus T is equal to the net weight, 3A. And in the question, A has been provided as what? 2 meter per second squared. So if I have 30 minus T to be equal to 6, if I collect like terms, taking 30 to the other side, I will have minus T to be equal to minus 40. Dividing both sides by minus 1, because I'm not looking for negative tension, minus T, I'm looking for T. I will have T to be 40 Newton. If you also decide to use this one will now be tension minus 20 is equal to 4. So whichever one you use, you will still find your tension to be 40 Newton. Okay, so the next question says we should find the coefficient of friction. Beautiful. Now, for this plane, the net force along this plane, remember that tension is heavier than every other force. That is why T1 is able to move this mass of 2 kg closer to the right, thereby pulling the rope downwards. All right. So we'll have tension T minus 20 Newton minus friction is equal to the net force MA, right? Good. Is. All right. So we've gotten tension to be 40 minus 20 minus F is equal to what? Equal to 4. Because our mass is 2 and our acceleration is 2. So 40 minus 20 will give us 20 minus F is equal to 4. So if we collect like terms, minus F is equal to minus 16. So to find friction, divide both sides or multiply both sides by -1. So our friction is 16 Newton. Okay, so to find the coefficient of friction, we have our mu to be equal to the force of friction over normal reaction, which is 16 over mass times gravitational force 10 cos 40. So we have mu to be equal to 16 over cos 40 will give us 0.76660. So we have, if you have your calculator, let's do it together. 20 times 0.7660, that will give us 16 all over 15.32. So we have our coefficient of friction to be equal to 16 divided by 15.32, and that will give us 1.044 approximately. So I believe that with these examples, it is clear to you on how to solve questions on motion uh, of connected particles. So please feel free to reach out if you have further questions or you need more clarifications, and see you in our next video. Bye.